Okay, so as I said, the goal of at least this approach doing it is to compute the likelihood ratio. And I want to compute this for all possible values of amplitudes, initial phases, and frequencies. And I want to find out where you get the maximum of this quantity. Okay? So to help us to do this, let's do this little trick. So we have the signal in this form. Let me just expand this sign and write the signal in this way. So it's A1 times some H1, then A2 times some H2. So where I just expand it, I say that A of sine of this times sine of that plus A times sine of this and cosine of that, and then the other way around. Okay? So then the amplitude A1, A2 are combinations of this amplitude and this initial phase. And this H1 and H2 are just the sine and cosine of this 2 pi f naught times t. Okay? So sounds very trivial, but the important thing now is that I have two kinds of parameters now. So I have the parameters of amplitude and the initial phase, which appear in these amplitudes here. And then I have the frequency, which appears within the phase. Okay? And moreover, the H depends linearly on A1 and A2. How does it help us? Well, let's look at now this log of lambda in terms of these parameters here. So now it's obvious that this log of lambda is quadratic in the signal, in this term, and is linear through this term. So the end result is that log lambda is a quadratic function of these amplitudes A1 and A2. Therefore, I want to find the maximum of log of lambda, so I can simply maximize over these amplitudes, just simple differentiation. So that means I write my log likelihood in this form. It's some AI times some xi. I goes from 1 and 2. And then some matrix times AI and aj. So it's a quadratic in the amplitudes. So in this special case of this simple signal model, the matrix is diagonal. The diagonal entries are just T up divided by the spectral density. And the x1 and x2 are just the inner products of the data with these two basis functions, h1 and h2. So now I'm in good shape. I have this quadratic form. I just want to maximize first the log of lambda over these amplitudes. So I just differentiate that with respect to AI. Then I get this linear equation. I can just solve this for the amplitude, and you get m inverse times the x. Okay. So this means I have found my best fit values for these A1 and A2. That means best fit values for the amplitude and the phase, initial phase. And for this, I did not have to do any numerical calculation. This was completely analytic. So then I put these best fit values back into the log likelihood function. So I have here the best fit values for these A's. I substitute this back in here. And then you convert your log of lambda to something known as the F statistic. So this is a notation very specific to gravitational waves. So I don't know why this is called the F statistic, but that's what it is called. I just take the log of lambda, substitute the best fit values for the amplitudes, then I get a quantity which depends only on the frequency. Okay? So, and now the goal is simple. This f here depends only on this frequency f naught. So then I just have to compute this f for all values of f naught and find the point where it's maximum. Okay? So in this procedure, then I have found for you the frequency, and by the other maximization, I have also found the best fit values for the amplitude and the phase. So written more explicitly, this F statistic is an expression of this kind, So this is simply x dot h1 squared and x dot h2 squared. And if you think about it, this is just complex, right? So this is just this quantity here plus I times that, and then the square. So it's h1 plus I times h2 multiplied by x. And that is simply the Fourier transform of x. So that's a short little one line calculation to understand that. And then the end result is that to compute then the F statistic, it's what you might expect. I take the data, take its Fourier transform, look at the modular square of that, and find out where that is maximum. So I suppose even if you hadn't known anything else, if I have the data and you expect a sinusoidal signal in there, you would just do a Fourier transform and find where that is peaked. And that is what this analysis tells you as well. It gives you a bit more. It also gives you the amplitudes A1 and A2, or the amplitude A and the initial phase phi naught. Okay. And this prefactor here tells you how loud the signal itself is. Okay. So the smaller the noise, the larger then the significance of the event. So again, just to recap what we've done today so far. So we looked first at the general problem of finding a signal. We got the likelihood ratio. I motivated that for you through the Neyman-Pearson criteria. And then we applied that for this very simple case of a sinusoidal model. And then that led us to the fast Fourier transform, leading us to the F statistic in this way. Yeah.
This is only used in gravitational wave stuff, not why? This is just statistics.
No, it's using, I'm just in notation, so the F statistic. So then there's the notation. A lot of these things are rediscovered in gravitational waves, and statisticians have known about this much longer. But still, papers have to be written, so, and people aren't aware of everything that's been done. So it's rediscovery of many things with different names. So the F statistics is possibly one example of that. So let me spend a little bit of time briefly on an alternative to all of this, which is the Bayesian approach. So as I said, the frequentist approach relies primarily on this likelihood function, which is P of x divided by P of x given noise. Okay? And the important thing is that this mu is treated like a constant. So you're not allowed to think of mu as a random variable, right? Just a constant. It's a constant, and you got to find the best estimate for this constant. So that's the motivation. In practice, though, I mean, mu is just not known, and you can take a bet what its value will be. So you can treat mu also like a random quantity. Okay? So therefore, you can write a distribution for mu given the data. So this is not something a frequentist would ever do. So I mean, the frequentist will agree that this relation is true if mu and x are both random quantities. But a frequentist will never write a distribution like this for something that he believes is a constant. But again, if you assume, if your viewpoint is that this mu should be treated like a random variable, then you are free to write this. And then you apply Bayes' theorem, and then you go from this to this quantity here. So in which you have the distribution of the data given mu and of the data given just noise. And you get this distribution of mu itself, which is the prior distribution of mu. Okay. So what you then have is you have P of mu multiplied by this likelihood function. So once again, even with this approach, you still need to compute this likelihood function. I mean, that is really a very important thing. But a Bayesian would say, I take the likelihood, I multiply that by my prior information on mu, and the result is the posterior distribution of mu. Okay? So in this framework, the business is that you have some information on mu that is contained in the prior. You do the experiment. The prior gets modified by the likelihood, and the result is then the posterior distribution. And this distribution contains all the information about mu that you could possibly extract. From this, you can compute its mean value, you can compute its most likely value, you can compute the error bars, the standard deviation, and anything you want. Okay. So the other obvious thing is that if this mu, P of mu is a constant, so let's take a uniform prior on this quantity mu, and ignore for the moment that mu could be an infinite domain, so that the P of mu has to be, should be a normalized distribution, but in that case it wouldn't be. Ignore that for the moment, then it's clear that the posterior is then just the likelihood function in this approximation. So then in the case when you have a uniform prior, then both of the bases and the frequencies would only compute the likelihood function and look at where there is a maximum, and that gives you the best fit values for the parameters. Okay. So let's do this simple exercise for the simple model that we have so far. It's easy enough to do actually. So let's take a uniform prior. Okay, just the fact that you can do the integration. So what you would end up with is you would have a posterior on A1, A2, and this frequency F0. So what a Bayesian now would do is that you want to find a distribution for F0. How do we go from the distribution for A1, A2, and F into just something on F? Well, you eliminate A1, A2 by doing this process of integration. You average the distribution over these unwanted parameters, let's say. Okay? So as a very rough caricature, a frequentist likes to differentiate, a Bayesian likes to integrate. Okay? So a frequentist would like to find the point where this is a maximum in A1 and A2. That is what we did, in fact, previously, right? While a Bayesian will say, I want to average over A1 and A2. And in fact, you might argue that the Bayesian one is better because you get more information from doing this integral over the full distribution and not just the distribution near its maximum. So then we can do this with this operation. We can actually take this likelihood function, a times x plus this quadratic, and I can actually integrate that because I can integrate a Gaussian function. So then what I get then is this posterior I can write in this form. I can separate variables. I can write it as a quadratic piece in A1, a quadratic piece in A2, and exponential of something that turns out to be exactly the F statistic. So again, this is like a 2 or 3 lines of algebra, then you get this expression here. And then when I integrate over A1, A2, both of these terms go away, and I'm just left with the exponential of the F statistic. So even in this Bayesian procedure, what you get is that the posterior distribution on the frequency is exponential of this F statistic. So once again, you just need to compute the F statistic, and you want to find its maximum to determine what the likely value of this F of the frequency is. And moreover, the width of this function gives you the error bars on the frequency. Okay, so is the procedure clear? This is a very simple model, and of course we'll go to more complicated case in a minute, but I want to be sure that you understand this simplified case at least, in the both frequentist and in the Bayesian frameworks. Any questions at this point before we move on? Okay. So there's, of course, all of this simplification does not happen if the priors on your frequency are not uniform, then it's more complicated. But I won't go into that detail here, so let's just leave it. Let's just leave it at that for the moment. And let me also skip over that part. So let me now go to the gravitational wave case. So now the case that we have is not this simple model that we have, but it's close enough actually. So what we have is some beam pattern function f plus, depending on the three angles I talked about earlier, times h plus the other function f cross times h cross. Okay. And we saw that h plus and h cross can be written as a slowly varying amplitude and a phase. Okay. So then once again, so I remind you again how we got this h plus and h cross. Okay. So remember, h plus was this eta of t times a plus times cosine of phi, and h cross is eta times a cross times sine of the phase. And once again, the phase equal to some initial phase plus other things. Exactly like we had in the simple model. And once again, you want to expand the cosines and the sines by simple trigonometry. Okay. In this case, however, you'll get two terms coming from here and two terms coming from here. So you get, combine them with f plus and f cross, you get four terms in the end. And not two like we had for the simple sinusoidal case. Okay. So as I said, you write your phase as phase or function of time plus some initial phase, and you expand this in the h plus and h cross with simple trigonometry, and then what you end up with is this expression here. You get your signal in any given instrument detector I to be the sum of four terms. So previously, remember, we had two terms, right? For a simple sinusoidal case, you had a times cosine and a1 times h1 and a2 times h2. In this case, we have four terms because you have two polarization, and for each polarization, you have these two terms. Okay? And the exact expressions for these, what these a1, a2, and a3, and a4 are, that you can easily work out by simple trigonometry, and you get these, tedious but easy enough expressions for these amplitudes. And you also get expressions then for these basis functions h. In each case, they are something connected to the beam pattern, the detector response, times a cosine, and something times the sine. Okay? So I don't expect you to understand this algebra just by looking at the slide for like 30 seconds, but it should be at least be clear that you get four terms and not two terms like before. And the important point is that in this expression, these amplitudes are independent of the detector. And only the basis function depends on the detector. So if you have a network of n detectors, for each detector you can expand the signal in this way. And the important point is that then these amplitudes do not depend on the detector. So just to convince you of that, so these are the expressions for the amplitudes. So the way you do this is that if you have n detectors, you set up a reference frame at the center of the Earth, for example, or for the continuous wave case would be in the solar system barycenter. But doesn't matter, some common reference frame for the n detectors. In that common reference frame, you define this angle psi and this initial phase phi naught. And then, of course, you got to transform from that frame to each of the detectors, and that is what is done by the rest of the procedure. But it's done automatically, so to say, in this case. And then what you end up with are these amplitudes, which are independent of the detector. So that means that when you write down the likelihood function for this data for all the instruments, you can still maximize over these amplitudes the same way as before. And you just have these four amplitudes that you should maximize. Even if you have one detector, two detectors, well, one is a degenerate case, but let's say you have some two detectors or three or four, whatever number of detectors. Yeah.
We have three detectors at most?
Yeah, so we have the two LIGO and the Virgo detector, yes. And in the future, with LIGO India, Kagra, we can have 5 detectors in the near, well, not too distant future, let's say. So this, yeah. Yeah, Virgo is functional, yes indeed. Virgo is completely functional. I don't know the latest on the sensitivity of that. Others can tell you better about that for the latest information, but yeah, as I understand, all 3 are functional. So continuing then, for each of the instruments you have this power spectral density, and then your inner product is now a sum over the product for each of the different instruments. This now assumes that each of the data for each of the instruments is independent. So that's how you can sum the likelihood over the different instruments separately. And when the procedure again is clear, once again you got to maximize first for these amplitudes the log likelihood, put the maximum back into the log likelihood, then you get the F statistic, and you compute the F statistic, and that is what you should do to find a signal from any general network of detectors. Okay? So I won't go into the details of how you do this and what are the sort of error bars from the scar location and the masses and spins and what have you. So instead, what I'm going to do is I'm going to, in the remaining like 20 minutes, I'm going to just go back to the first binary black hole detection where we started all the series of lectures and tell you how is it that we compute the significance of that event. Okay?
You don't mention how this improvement to see about 10 to the 5 of a proton size with the latest improvement of instruments. I mean, where are they located in this scheme?
That is something I'll leave for Nergis to talk about in detail. I mean, that in this scheme, I just have this power spectral density, right? I have this noise function, and for me, it is whatever the instrument gives me, and I have to work with that to the best of my ability. And about how good that is, I mean, that is beyond my abilities to really tell you, and you will, but I'm sure you will hear a lot more about that in the next lectures. Okay, but what I want to convey in this is that given any network of these detectors, each with its own power spectral density, each with its noise properties, this is sort of, at least for the simple case, an optimal way to combine the data from this whole network and get them the result. Right. So what was done, in fact, in the first science run for the O1 analysis is not quite what I described just here. Okay. It was an even simplified version of that. Why? What I described for you was what is called a coherent search. It's how you combine the data from different detectors all coherently. Okay. This whole process of the likelihood function and everything is great. I mean, automatically it gives you full coherence of the analysis between different detectors. Instead, what was done even now what is done for the most part is that you treat each instrument independently. Then you get a list of events for each instrument, and then you apply a coincidence step of candidates between these instruments. So this has many practical advantages, and the important point is that for 2 detectors, you can improve this coincidence to a level which is almost comparable to a full coherent analysis. So at least for 2 detectors, you get the same benefits of the coherent search in a much easier, practically easier analysis method. Okay. But again, now let's look at the case for a single detector then and repeat the procedure for the F statistic. So the log likelihood, again, is the same expression. Assume that I have one overall amplitude A. Okay. So log likelihood is then A times this inner product minus A squared times that. Again, the same thing again and again, right? I maximize over this amplitude. Then the best fit value for the amplitude is just this expression here. I put this back in the log likelihood. I get the F statistic, which again is simply, now for the single detector, I just have one basis function. So it's simply one Fourier transform squared. So same procedure, I just applied this to one detector now. Okay? But there is one simplification now that you can do, and which is extremely important, which is I want to now consider these binary black hole signals, but they can arrive at any time. Okay? So I want to search over this time of arrival, again using a fast Fourier transform. How do I do that? Well, it's easy. If I shift a signal in the frequency domain in time, I just get a phase multiplying it. So when I want to compute inner products of this kind for different values of t, this is the same as computing this for some t naught equal to 0 and then doing a Fourier transform. And that results in then this quantity for all values of this t naught. Well, it's an inverse Fourier transform in this case. Okay? Anyway, you can use the FFT algorithm. That means the search over time is done through an FFT.
Usually you just look at the coincidence at two places which has very similar wave shapes and so on, and you don't mind about all these calculations.
No, this is very important. So this is key. Because for each instrument, right, we have these waveform. I want to find the inner product of the data for each instrument with a particular model, right? So therefore, and for I don't know the arrival time at each of the detectors, and I'm looking at them independently. Okay, so therefore, for each instrument, I want to take all the possible models that I have, all the possible templates that I have, that goes in here, and I want to find this inner product, and I shift each of these in time, and that is this Fourier transform. And then I will explain the procedure in a little bit of detail in the next slides. So let me just go through that. It should become clear. Okay. And then the other thing that you can do also is maximize over the phase. Again, the same thing like before. So if x is something times cosine and the sine, the maximum in term over the phase is just the sum squared of x1 and x2. And this, again, you can convince yourself easily enough. Okay? So the procedure then is simple. I first search over the time by Fourier transform, and I search over the phase, I maximize over the phase by computing this norm, like this. Okay? And the result is a quantity which I'll call z of t, t0. And then I want to look at the z of t0 and then see at what values of t0 I get loud events. So let me skip over that. So this is the general pipeline. Again, I don't expect you to go through this easily. But there is one thing I do want to explain. There's two things I should tell you now. The first is what is called a template bank. Okay? So if I go back now to this picture here, right? So the procedure, at least I hope, is, the details may not be clear, but at least I hope the basic idea is clear. For each instrument, I need to search over this time of arrival and the phase. And I want to do this for each of the points in parameter space. So for each value of the masses and spins, for example, I got a particular waveform. I can check whether that particular model matches with the data or not. Of course, this parameter space is continuous. I have masses and spins. I have to discretize in some way. Okay? So to pick some finite number of points suitably chosen in this parameter space, and for each of these points, I get a waveform model, and that I will match with the data. And what was used in the first science run was exactly this template bank here. And what is shown here is a parameter space for the masses. That's M2, and that's the primary mass M1. I mean, this is just M1, M2 switch, so I'll just look at them this quadrant here. This region here is the low mass, that is the neutron star binary parameter space. This part is the high mass, that is the binary black hole parameter space. And this part is the neutron star black hole parameter space. And these dots represent the actual templates used in the first analysis.
Yeah, that's not curves.
Sorry?
Each is a point.
Yeah, each is a point, yes. These are the different templates used in the analysis, yes. And what is shown here also are the best fit templates for the first black hole detection. That's this one. Then and this was O1, remember, so we just had 3 detections in that case. The two loud ones were picked up by these two templates. And we had two independent pipelines using the same template bank. And they agreed for these loud events, but they disagreed for this event here. So they also reported an event, but they had a slight disagreement which template was it that maximized over this. But it doesn't matter, because the goal of this part of the analysis is just to see whether you have a signal or not. Then the next step is to estimate the parameters, and that I will not describe here, just the surge aspect of the whole thing. Okay. So there's one very important thing that is still missing, right? So what I've described for you so far is what you would do for the simple case when I have Gaussian noise that is stationary and has all the nice properties that follow from that. The real data, as you've heard many times, is not Gaussian, it's not stationary. So how can you possibly expect the simple thing I described so far can possibly work with real data with all of its complications? And the answer is that it wouldn't work, actually. So if you just blindly followed everything that I told you so far, applied it to the real data, you would never ever detect, well, the first one you would detect, but any of the others you would not find. And for this, there's one missing piece, okay? And this is a result of a lot of people's work over several years. I can condense it down to one slide, and that this is completely unfair for this amount of work that has gone into this, but well, that's how much time I have here. So the point is that you want to do something more to each candidate to check whether it's a real signal or not. So normally, if the data is just Gaussian and stationary, anything more that you do to the events, you're always guaranteed to lose, right? And that's because the Neyman-Pearson, essentially, well, there's some complication, but essentially is this Neyman-Pearson lemma. That's the optimal thing to do is likelihood function. Anything more that you do, you're going to lose. But again, the actual data is not Gaussian, it's not stationary. Therefore, you could win if you did something smart. And that smart thing is the following. So what you do is, I have a given template. It covers a frequency range from, let's say, some f1 to f2. Okay? What you can do is you can break up this frequency band into subbands in such a way that if the signal were real, each of this frequency band would give the same power. Okay? So to illustrate that, just look at this from a paper by Bruce Allen back from 2005. So this is a simple case in which what is shown here is time of arrival, and this is this quantity z of t for the 4 different frequency bands in this example that was done. So if you have a real event, that is what is called a simulated churn in this case, for each of these sub-bands, you get a peak at the right time in all the different filters. And with roughly the same amplitudes in each of the filters. Don't worry about the data, just look at this time t0, just look at the peaks here, is roughly the same, is roughly the same, same, same. And they all peak at the right time, okay? So again, just to recap what that means. I take a template, okay, which is just some function of time, right? I convert that to the frequency domain, so that's some function of frequency that I should match with the data in the frequency domain. Now I break up this template in the frequency domain into 4 different frequency bands. In such a way, this I choose beforehand, that each of the bands should have the same power content for a real signal. So therefore, for each of these templates, in this case, I get 4 of these sub-templates, if you want. And I can repeat the analysis for these 4 different sub-templates. And for a real event, everything should be consistent. But if we have what is called a glitch, so that is like a spurious event, also quite loud, what you will find is that some of these bands contribute a lot more than the others. In other words, this is an empirical thing in this case. It is found that for most glitches that we have in the detectors, they differ from the signal in this property, which is that they don't have equal power in these different bands. Some bands are much louder, some bands are much weaker. Okay? So then the procedure is clear, right? So what we do then is that for each of the instruments, we do the ideal match filter that I described before, apply this test, what is called the chi-square test, and then see if it passes the chi-square test or not. If it passes, then I say I have a candidate from detector 1, some from detector 2, and then I do the coincidence between them. Okay, is that clear? So, or to put it differently, right? For each candidate that you have two values that you computed by this way. You computed the signal noise ratio, that is the usual procedure, and you computed this chi-square. And I want to combine these two quantities to get something called a ranking statistic for each of these events. So the goal in all of this is to get, for each get a number which says good or bad, right? The larger the number, the better. What should the number be? And again, this is a work of a lot of people over several years, condensed into this equation here. I cannot explain to you why it is that equation, why that power 2 and then why that power 3 and then 1 over 6 and so on. Thomas Den could, but I couldn't. But that's how it is. But the point is, I want to convey is that you have a way to rank candidates for each instrument based on the SNR and on the value for the chi-square. Okay. So now let's finally go now to the calculation of the statistical significance of the events. So let me again focus just for concreteness on the first detection paper. This was 1509-14. So what is done there is the following trick. So this is now the last thing I want to explain to you before we stop. So think of it this way. So in that case, I have the Hanford and Livingston detectors. So let me solve. This is now time. This is, let's say, H1. This is time. This is L1. Then I have some events at some random times for Hanford. This happened at these times. Okay. And then I want to see whether this event here is coincident with an event here or not. If it is coincident, I just combine the values of this new SNR, this strange SNR I described just now, and then I get a final statistic for that combined event. Okay? But we are not done yet, right? Now you have to answer the question, if there were no signal, how loud would these random coincidences be? Because in the end, it's not enough to just compute this statistic for each of the candidates. The number could be 10 or 20 or 50,000, right? How do I know how significant that number is? How do I know that if I just did not have a signal, just by chance, I could get a number as loud as that? And to do this, you do the following trick. I take the list of candidates from Hanford and from Livingston, and I shift them in time. And I shift them in time by an amount larger than the light travel time between the two detectors. So once I've shifted them in time, let's say I shift this one in this way, and this one in time in this way, and then I do a coincidence, then it is obvious that any coincidence I get cannot be a real event. Okay? So by repeating this procedure for different time shifts, I get a list of the background events from the analysis. And this distribution, then I can then evaluate how significant from the real list of events each event is. Okay, so just to quantify this a little bit. So for the first detection paper, that was February of 2016, so we used 0.1 second time slides, and by effectively we had about 50 days of data. By doing these slides of time, each by 0.1 seconds, effectively you got a background time of about 600,000 years.
Why do you use 0.1 second while the light travel distance is much smaller to detect?
Yeah, exactly. So we use some larger than that so that we get this is then the background calculation, right? So if we use a time shift by this much, then we're guaranteed that any coincidences are spurious. That is the background.
Between 6 milliseconds to 0.1 second. In that interval.
Oh, that. Yeah, we could take a smaller value, yes, but again, you want to be safe. I mean, the whole and just to say, so we picked this 0.1 second. We had 16 days of data, and if you just do the numbers, we had to get 5 sigma. Okay, so this essentially boils down to the fact that we have to decide beforehand how much data do we need to get a 5 sigma detection at the end of the day. Right? So this was chosen beforehand based on that criteria.
Then what does this 600,000 years?
Yeah, so this is the effective time, right? So what it means is that I have the list of candidates. I shift this in time by 0.1 second. I get a new list of candidates. That covers again the same amount of data. Shift it again by 0.1 second. I get one more list of candidates for the same amount of data. How many times you can repeat this? I just get artificially more and more data. And the effective amount of time turns out to be, for this duration of data we had, 16 days, and this amount of shift, 600,000 years.
Is that enough to be sure?
Yes, so I will show that this was actually enough, yes. So, the way that works out is that if you just compare the 0.1 second and then 600,000 years, you can just convince yourself that all the 0.1 times 0.1 second slides that can be done over 16 days gives you, at the best, a smallest probability of 7 times 10 to the minus 8. And this, if you convert to a significance like a Gaussian distribution, is more than 5 sigma.
After all these efforts, is 5 sigma enough? Most of the effort, it should be 10 to 15.
Well, what can I say? I mean, we were told 5 sigma is the gold standard, and we said, okay, that's what we'll give you then.
You did more than that, I believe.
You're always going to be catching the most events are going to be the ones that are right at the threshold, though, right? So you hope you're going to get that one golden 38 sigma event, but most of them will be right at that threshold. So.
Indeed, yes. I mean, if you were to extend this for the full 4 months of O1, you would get a better number. But there's still a limit, right? I mean, the goal was, look, we had the first detection, right? And we want to say, we don't want to wait for the full data run to finish and then do the analysis and publish, right? So we want to say we want to publish as soon as possible. So what's the smallest amount of time that we have to wait before we can do the analysis? And then we said, okay, let's try to reach 5 sigma. And then by this procedure, we calculate that we need 16 days of data. So that then fixes 16 days, and that is the 5 sigma.
You mean you aimed 5 sigma,
Yeah.
and then found that you need 600,000 years.
That's right.
Okay.
Yeah. And this is the result of that analysis from the first detection paper. Of course, you can find updated plots of this for O1, the full O1, and this full O1, then for O2, and so on. So this is for the full O1 set now, not just the first detection. Okay, so but the same procedure applies also there. So let me describe all the different curves in this plot. The first thing is if you don't do any time slide, you get a list of events, and for each event, you get a value for this detection statistic. Okay. So you have one event with a detection statistic of like 22 point something. You get one event with about 13. You get one more event, a little bit less than 10, and you have the whole tail of events below that. Okay, at least the orange squares are clear, right? Now you repeat this with these time slides, and you get a list of events once again. This is your background list of events. And this first curve shows you that. So once again, you get a whole tail of a bulk of events deep in the distribution here. It continues, and the tail you get this quantity here. So the loudest event you get by this procedure in the background is 20 point something, which is lesser than the value for rho for the first event. And this is unprecedented, right? So from this huge list of background events, we still were not able to get something as loud as the first binary black hole. So that means that for this event, we can actually not measure its significance accurately. We can only say that it is bigger than this 5.1 sigma value. Good. But now you can go further, right? So you can say, well, this event I'm sure is a real signal. So now I remove that from the list of candidates, both in the actual set of events and from the background. Because remember, when I do these time shifts, it will happen that I have an event in one detector, which is coincident with some noise in the other detector. And these events are, in fact, exactly of that kind. So when I want to estimate the significance of the second event, what I do is that I remove this. I'm sure now this is a real event. I remove it from the list of candidates, and I repeat the procedure. That gives me then this line here, this background. And so in here, this bar corresponds to this event, and this one corresponds to this event. This is measured based on this background. So the second event was in fact also close to 5 sigma, but based on this other background in which I excluded coincidences arising from the first event. Third, it doesn't make a difference after that, because this is really in the deep in the towards the Peacock distribution. So the coincidences of this with noise in the other will remove maybe this little bit here, but it doesn't really affect the significance at this value of this detection statistic. But still, in this procedure, you can estimate this to be roughly 2 sigma. And again, further analysis later is the one that convinced us that this was a real event. In this publication, this was still a candidate event, wasn't a real event, because this is not very high in sigma.
I mean, not only the instrument, it's the analysis really itself. Something has to be priced in.
I mean, again, I'm describing the work of a lot of people over like 15, 20 years, right? So it's, I can only explain so much in the time, but at least I hope I give you a flavor of the kind of thing that is done. And I have not even talked about the parameter estimation side of things. How do we estimate the parameters? I mentioned briefly the Bayesian stuff, but again, we don't have time to go into the details of that. But I thought you should see, at least in some detail, how is it that we are sure that these events we see are real events. Yeah, so this is again the same procedure, but this is the one when I excluded 150914, and I got the other event. Then I excluded that to get the significance of the third event. But again, so that was it. So I'll stop here. So in the 4 lectures, we covered the basic properties of 2914 and the continuous waves. We did the quote-unquote boring part of the signal processing and the statistics, but I hope you learned something in that. And I gave you some details of the binary searches and the significance estimation. Okay? So I'll stop here and we'll take questions.
Questions, please. Would there be any point of line or input detectors that reach to the value of 10 to the minus 25 that you showed us? Like 1 order of magnitude over it?
Oh, for the maybe I should clarify that. For the continuous waves, this h naught, right? I mean, it's 10 to minus 25. That is not the strain. That is its amplitude. So that factors in the full observation time of the data. So you shouldn't compare that directly to the strain sensitivity there. So that is special for the continuous wave because you integrate really for a long time, so you can dig much deeper in the noise.
You said you're shifting 0.1 seconds. What's the time resolution of the detector? Because it should be a multiple of it, right?
Yeah, so that is, it doesn't have to be multiple of that. So I don't think it does have to be multiple of that. Is much finer, of course, the time resolution. The times, you mean the timestamp on each data point that we have, that's what I mean, right?
But when you shift it, it should coincide so that
Oh, I see. So I didn't describe one step, which is a clustering step. In other words, what happens is that we have, you should think about it. We have for each instrument, we have this SNR, right? So it's positive, so we get some large values. And then we set a threshold, and then we cluster events above a given threshold. There's a procedure for that, but the end result is some time interval for each event. So it's not of one, just one time. So that's.
Practically, we have data in array format, right? It's a vector.
Yeah.
So if I find the covariance matrix of this vector data, and then if I find the SVD of this, and then at the threshold value, I cut the eigenvalues, and then take the projection, and then look at the cosine similarity, isn't it going to work instead of?
It might work, yes. A lot of people try similar things, indeed, yes. So
it is worth to try. Right?
it is worth to try, yes. I mean, the details we can discuss, but the general idea is worth to try, yes.
I have 3 questions. So the first one is, what do you do when you have 2 or more detectors in the time sheet?
Oh, okay. So, okay.
Second one is there are there common priors for the event parameters used in different searches? So like all of them use the same priors. And final one is you mentioned the semi-coherent search with Einstein and Tom.
Yeah. Oh, I see. Okay. So let's take the last reverse order. So the semi-coherent searches, again, is one of those things where something I spent sort of many years working on, but I'm sad that I can't present the details to you. So the way that works is the following. So you have the full time series, right, from, let's say, one instrument in this case. So, and the bottom line is that you cannot do a match filter over the full year-long data set. So what you do is that, but you can do divide and rule. So we can do sort of the match filter for some amount of time. Let's call it delta t. And I'll repeat this for different delta t's till I cover the full observation time. Okay? And then I have events from each of these different segments. Of course, in the continuous wave case, the signal is Doppler shifted across the different segments. So I know that for a given signal, how much the Doppler shift will be in frequency. So in the frequency domain, I know that a given frequency here should end up correlating with a given frequency here. So then I combine in some way the different frequency bins for these different detection statistics from the right frequency bins, and then a sum over this track in the time frequency plane. So in this way, for each template, I combine the different segments and I get a final detection statistic, and that is the thing that I use to claim a detection or not. Okay? So that, at least roughly speaking, is what the semi-coherent searches are. So the second question was the priors, right? So so that is more, I mean, in this thing that I described with the searches, estimating significance, there is no assumption of a prior, right? There is the template bank that is used. I mean, you can say each template bank is as likely as any of the others, so it's like a uniform prior in that space, if you wish. But the way the prior that comes in really is for the parameter estimation. So when you describe the Bayesian method, at least very briefly, so in that case, you have to take the likelihood and multiply by the prior, and then you get the distribution for the posteriors. And that then depends upon what your astrophysical priors are. So for example, if it's an angle for the spin orientation, that's a uniform prior. If it's the spin itself, and you say it's neutron stars, then you want a prior which is low in spin. Or for a black hole would be much larger range in the spins. For the masses would cover some astrophysical range that you believe that you can detect or there exist these systems. So that is complicated, but that again is a okay, everybody does not do the same prior, but there is some sort of common features of these priors there. Okay. Then the first question was the could you for 2 or more detectors? Yes, it's the same in procedure, same in principle, right? So you have not just 2, you have 3. So shifted by enough so that no coincidence can be real. But you can do many more. Of course, there's combinatorics that you have to do in that case, but that, it's just a matter of working it out. But it's same in principle. But I would say that for 3 detectors, it is really worthwhile to do the full coherent analysis I described with the F statistic.
Did you do this analysis for this neutron star which
Yeah, indeed.
and what was its significance?
No, this was in O2, right? So that is, no, I don't remember the significance. Stopped caring about that after a while, to be honest. It was so loud that I'm embarrassed. I don't know the number for you, but I can tell you.
If no other questions, let us please thank